In the twilight of the 19th century, the edifice of classical physics appeared to many of its practitioners a nearly complete and magnificently coherent structure. The laws of mechanics, thermodynamics, and electromagnetism described the universe with a majestic and deterministic precision, yet, within its final, unplastered corners, unsettling spectres were beginning to stir. With Huntington's 1895 discovery of X-rays, a mysterious form of radiation that could penetrate solid matter, was a profound shock to the scientific consensus. It was in this atmosphere of expectant curiosity that Henry Becquerel, 1896, stumbled upon a related phenomenon. While investigating the connection between phosphorescence and these new rays, he found that uranium salts emitted a penetrating radiation of their own, one that emanated spontaneously and persistently, independent of any external energy source. Becquerel had opened a door, but he remained standing at the threshold, observing a curiosity. It took the focused genius and methodological rigor of Marie Skłodowska Curie to stride through that doorway and begin a systematic exploration of the world beyond. Her 1898 communication to the French Academy of Sciences, titled on a new radioactive substance contained in Pitchblende, represents a seminal moment in the history of science. This concise paper, presented on her behalf by her former Professor Gabriel Lippmann, was far more than the announcement of a potential new element. It was the articulation of a new scientific paradigm, a fusion of quantitative physics and analytical chemistry that defined radioactivity as an intrinsic atomic property and, in doing so, effectively laid the cornerstone for the nuclear age. The genesis of Curie's investigation lies directly in the intellectual inheritance of Becquerel's discovery. Where Becquerel's work was qualitative and serendipitous, Curie envisioned a research program that was systematic and quantitative. She sought to determine if other substances shared uranium's peculiar quality. This ambition required a tool of exquisite sensitivity, an instrument capable of measuring the exceedingly faint electrical currents produced as the radiation ionized the surrounding air. Providence had placed such a device within her reach. Her husband, Pierre Curie, along with his brother Jacques, had some years earlier developed the piezoelectric electrometer. This instrument utilized a quartz crystal which, when subjected to mechanical stress, produces a measurable electric potential. By applying a precise weight to the crystal, one could generate a charge that exactly balanced the current created by the radioactive sample. The rate at which this balancing weight needed to be applied provided a precise, numerical value for the intensity of the radiation. This was a crucial methodological leap. Becquerel had used photographic plates, which offered a binary. He saw no indication of radiation. The Curie electrometer transformed a mysterious quality into a measurable quantity, empowering Marie Curie to conduct the first ever systematic survey of radioactivity across a known chemical landscape. Armed with this powerful apparatus, Curie began a painstaking examination of all known elements and a wide array of minerals. Her initial findings, reported in a preliminary paper in April 1898, were themselves revolutionary. She confirmed that thorium also emitted these rays, and she established the single most important conceptual foundation of her entire research career. The intensity of the radiation emitted by uranium compound was directly proportional to the amount of uranium it contained. The chemical composition, the physical state as a solid or in solution, the temperature, and the exposure to light were all irrelevant. From this, she drew the audacious conclusion that the ability to radiate, which she termed radioactivity, was an inherent property of the uranium atom itself. This idea was a profound departure from 19th century chemical philosophy, which viewed the atom as the immutable and fundamental building block of matter. Curie's hypothesis suggested that deep within the atom lay a source of phenomenal energy, a process untouched by ordinary chemical reactions. It was during this systematic survey that she encountered the critical anomaly, the central puzzle at her July 1898 paper sought to solve. When measuring raw uranium ores, specifically pitchblende and chalcolite, she found their radioactivity to be several times greater than could be accounted for by their uranium content alone. A sample of pitchblende, for instance, exhibited an activity 4 times that of pure uranium. If her hypothesis was correct, if radioactivity was indeed an atomic property, then the only logical explanation was that these ores contained a small quantity of an unknown element possessing a radioactivity of immense. This hypothesis transformed the project. It was no longer a survey, it was a hunt. Pierre Curie, recognizing the profound significance of his wife's work, set aside his own research on crystals to join her in this formidable task. What followed was a Herculean labour that gave birth to an entirely new scientific discipline, radiochemistry. The 1898 paper on the new substance details their ingenious method. They began with several kilograms of pitchblende residue, a complex slag from which the uranium had already been extracted. Their guiding principle was brilliantly simple. They would subject this material to standard methods of chemical analysis, separating it into different chemical groups. After each separation, they would use the electrometer to test the radioactivity of each fraction. The radioactivity itself became the beacon, the analytical tool that traced the path of the unknown element. The process was a masterpiece of chemical detection. They dissolved the pitchblende and found that the active substance precipitated with the bismuth salts when hydrogen sulfide was introduced. This fraction, containing bismuth and the new active element, was intensely radioactive. Through a series of further fractional precipitations and sublimations in a vacuum, they concentrated the active substance further. Each step brought them closer, with the electrometer confirming that the radioactivity was becoming ever more potent in an ever smaller amount of material. They had cornered their quarry. The new substance possessed chemical properties analogous to bismuth, yet it was clearly a distinct entity, distinguished by its extraordinary radioactive signature. In their communication to the Academy, they proposed to name this new element polonium, a poignant and politically charged tribute to Marie Curie's partitioned homeland of Poland. This act of naming wove a thread of personal and national identity into the universal fabric of the periodic table, a declaration that science is an intensely human endeavour. The conceptual depth of the 1898 paper is belied by its modest and cautious tone. Presented to the Académie des Sciences, it laid out its logic with unimpeachable clarity. For the first time in history, the existence of a new chemical element was being posited based almost entirely on its radioactive emissions. The traditional proofs of discovery, a unique optical spectrum and a determined atomic weight, were absent. The amount of polonium isolated was so vanishingly small, a mere stain within the bismuth compound, that such measurements were impossible. The element's existence was inferred from its activity, a ghost in the machine of matter detected solely by its energetic signature. This was a radical epistemological shift. The paper's immediate impact was to electrify the small community of physicists and chemists studying radiation. It presented a clear, verifiable research program and a powerful new methodology. The work also contained a subtle but crucial clue for their next discovery. In their chemical separation, the Curies noted that after removing the bismuth and polonium fraction, a second radioactive substance remained behind with the barium fraction. This hint would blossom, just months later, into the discovery of radium, an element whose spectacular properties would ultimately eclipse those of its predecessor, polonium. The 1898 paper on polonium, therefore, served as the essential proof of concept, validating the method of chemical analysis guided by electrometric measurement and giving the Curies the confidence to pursue the even more elusive and potent substance lurking in their pitchblende residue. The reception of the Curies' work was a mixture of profound excitement and deep-seated skepticism. The idea of an element spontaneously emitting energy without an apparent source seemed to challenge the first law of thermodynamics, the secret principle of energy conservation. Luminaries like Lord Kelvin were deeply troubled, suggesting that energy might be absorbed from an unknown ethereal radiation permeating space. The definitive proof required isolation of the new elements in pure form, a task that would consume the Curies for 4 more years of arduous, industrial-scale labour in a leaky shed. The ultimate success of that effort, with the isolation of a decigram of pure radium chloride in 1902 and the measurement of its atomic weight, silenced the critics and cemented their legacy. The influence of the 1898 paper and the subsequent work it spawned radiated outward, fundamentally reshaping physics. The powerful alpha particle emissions from polonium and especially radium became the essential tools for other researchers. In the hands of Ernest Rutherford, these particles served as probes. His famous gold foil experiment, in which he fired alpha particles at a thin sheet of gold, would have been inconceivable without a potent source like that provided by the Curies' elements. The unexpected scattering of these particles led him to discard the a priori model of the atom and propose the existence of a dense, positively charged nucleus, thereby creating the modern picture of atomic structure. Furthermore, the discovery of a family of new radioactive elements, each with its characteristic rate of decay, led Frederick Soddy to formulate the theory of isotopes, atoms of the same element with different atomic masses. The atomic property Marie Curie had identified as immutable was, in fact, the signature of a subatomic process of transmutation, an alchemical dream realized through the cold logic of physics. In conclusion, The 1898 paper on a new radioactive substance contained in Pitchblende stands as a landmark of scientific achievement, a document whose significance extends far beyond the announcement of polonium. It represents a methodological triumph, demonstrating how the quantitative precision of physics could be masterfully wedded to the separation techniques of chemistry to forge the new science of radiochemistry. It embodies a profound conceptual leap, redefining radioactivity from a curious phenomenon to a fundamental and intrinsic property of the atom, thereby shifting the very focus of physical inquiry from the molecular to the subatomic realm. Finally, it was the substantive first step in a cascade of discoveries, providing both the blueprint and the impetus for the subsequent identification of radium and setting the stage for the complete deconstruction of the classical atom. In the understated prose of their communication, the Curies unleashed a revolution. The quiet, meticulous work of tracing an invisible energy through chemical residues opened a Pandora's box of fundamental forces, revealing that the solid, stable world of 19th century physics was built upon a foundation of dynamic, energetic, and ultimately transmutable atomic structures. This short paper did more than add a new element to the periodic table. It provided the first chapter in the story of the 20th century, a story that would be defined by the awesome and terrible power knock within the atomic nucleus.